I got this. Okay. Share. Stream it, baby. All right, here we go. Let's see. Okay. Hey, we're live streaming right now. Ladies and gentlemen, we're brought to you by SBCC Astronomy Program. All right. Thank you for coming today. Turn to your neighbor and say hello, neighbor. Good morning. It's not neighbor, it's morning, afternoon, right? Oh, man, you just kissed her hand. All right. Review is live. All right. Let's try this. Control V, paste it, and stream it. Review is live. Okay, here we go. That's 8 a.m. class. Just one more quick post to the. Oh, you guys can't see this. No, of course. Okay, because I'm on my laptop. I got it. I'm live streaming with my laptop. That's what I'm doing. Okay, here we go. How you doing? Are you guys doing? Nervous or are you okay? I think this is going to be an easier test, to be honest. But you're here to study, so you're going to do better, right? You're going to do great. Review is live. Okay, try it again. Control V, enter, and ooh, I think I'm posted right now. Okay, so I think I'm live. Oh, yeah. No. All this stuff is picking up in your head, but there's a number of ideas in here that I didn't really cover in class, so this is your chance to ask questions if you have any questions. But one of the things I really wish I would have shown you is this video clip. Can I show you the video clip real quick? So the video clip is a mission called the Cassini mission. You need to know the name Cassini, somewhere it's up there. Cassini, you see it? Cassini. All right, what is it? It's a mission to Saturn. It had with it a probe called the Huygens probe that it dropped onto one of the moons. Which moon? A moon called Titan. Okay, so you need to know that, right? And what's really cool about Titan? Who knows something neat about Titan? It's a moon with an atmosphere around it. This is kind of crazy. Imagine a moon with an atmosphere. That's what Titan is all about. So we're going to just look at this clip. And I think I go to the clip. Oh, here it is. Inspirational video. There it is. Landing.
Even at this period of 2004, and one of those so flawless and so perfect scenes, right? The most ambitious planetary station that ever built called Cassini aligned into orbit around the planet Saturn, and at that point, it became the farthest flying atmosphere in the ever established on our sun. Now, bear in mind, the second time is to get the spacecraft to Saturn as quickly as possible, so that those of us who are on missions are alive by the time the spacecraft gets there. By the time that the spacecraft is leaving by actually slowing down, and when I'm allowed to catch it for sun, I need to take pictures because this was as close to the rays that I had ever been before, and will ever be again, certainly in this mission, maybe even in our lifetimes. the most remarkable highlight to see exploration of Titan so far was the deployment of Titan's probe. And January 14th, the aerodynamically shaped flying saucer drifted on a piece of fabric to the hazy atmosphere of Saturn's largest moon and landed firmly on its surface. Numerous satellites in our solar system 10 times farther from the sun than the Earth and 7 times farther than the other planet anything before. The probe descended 2.5 hours through the atmosphere, and there's pressure, there's a temperature, there's transparency in the atmosphere. In September, and 2 days on the way down, this picture is taken at about 60 kilometers elevation. That is the altitude that a jet airliner will fly from the U.S. to Europe. So this is the view. We have your window of titanium airlines as we fly across the surface. And quite exciting. And it's finally arriving on the surface. And this is what the surface of Titan looks like. The first time we guys have ever seen it really. We found on Titan a remarkable place, remarkable surface environment, a strange Earth-like, and we are now looking at a remarkable 3 years in a row mission, perhaps even a decade of exploring Titan in the rest of the system. There's much to teach us about our planets, our solar system, perhaps even about the origin of life itself. My father's wish is that ultimately we will see many videos of our planet, so that these significant accomplishments of extending our senses and visiting the world will become as much of the fabric of our society as people who appreciate us. I think that this kind of media list will be much needed antidote to the constant reminders of bad news and even failure that we see all the time on television. And really equally constant countervailing reminder of the good and the glories that we can achieve if we set our minds to it. The exploration of our solar system is one of the signature enterprises of our time. We should be evaluated in all aspects.
I thought that video really, well, first of all, you guys see the picture of the moon and Avalon? Did it look like something you could have imagined on Earth? Right? So can I just quickly speak back to that? The bigger, and you're looking at the surface of Titan. So just to, I don't want to belabor it, but this is an important part of what you need to understand. This is another world, it's not Earth. But do you see anything that looks familiar? What do you see in the foreground? Bunch of rocks, right? Everybody see the rocks? Do you notice that they're smooth? Can anybody tell me what that means? There's weathering and erosion. These wash down a mountain, down a stream, and eventually settle right here. Now wait, this is really important. Are those rocks made of silicate? No. That's not what the mountains are made of on Titan. If you don't know that, you need to write down that the mountains on Titan are made of water ice. Those rocks are water ice rocks. You get it? This is a totally weird deal, but it's in fact just like on Earth. You have rocks. The mountain is made of rock, right? The weathering causes the rock to erode and crumble and come down the streams, right? And wash into this river or lake bed. And this has lakes and rivers and deltas and mountains and all the kinds of geometry that we see on Earth. It's foreign. It's alien, right? The mountains are made of water ice. What about the liquid? The stuff that's raining down on the surface and then weathering the mountains and then turning into lakes and rivers. What is it made of? Is it water? Now it's way too cold, right? So what is it? It's hydrocarbons. It's ethane and methane. Lakes of ethane and methane. The rock stuff is water ice, and the liquid stuff is ethane and methane. Like gasoline on it, right? It's like, imagine we're oceans of gasoline. All we have to do to fuel up our rocket is go there and tank it up. We're good to go. Right? So that's a part of what we need to know about Saturn's world. Really cold. So cold that molecules Yeah. We're starting at chapter 8. Chapter 8. Okay, so these are words that you're supposed to know. And actually, I want to throw in kind of why you need to know them. So maybe if you don't already know that, take them to know if that's the case. So what does the word stellar occultation mean? Okay, a star is being blocked, occulted, right? What is blocking it? Well, it turns out that particular term is actually related to the giant planets having rings. So the question is, how do we know that all of the giant planets have rings? We know about Saturn. Okay, you can see them. But what about Jupiter and Uranus and Neptune? They're dark. They don't shine with a lot of light. They don't reflect a lot of light. But how do we see them? Stellar occultation. When that planet is moving near a star, the star gets blocked out before the planet gets there. We saw the rings by stellar occultation. So that's actually a pretty cool idea. So that's in there just for that reason. The way that we found the rings of Uranus and Neptune and then later Jupiter was through stellar occultation. The light of the stars being blocked by the ring. The star is really far away. The rings right in front of the star and block its light. That way you could tell that there was something around the planet. Okay, next one, metallic hydrogen. How do people know what that is? Raise your hand if you know what that is. Metallic hydrogen, what is it? Hydrogen inside of which two planets? Two planets have metallic hydrogen. Saturn and Jupiter. Jupiter and Saturn, right? And why do they have it? It's a very special kind of hydrogen that's heavily compressed, really compressed, so that the atoms are so close together they begin to act like a planet. Now, then why do we even want metallic hydrogen? What's the point? To have the dynamo effect. Okay, so once we came up with this idea, once we finally knew that it was right, we had a mechanism for the dynamo effect in Jupiter and Saturn. So you could say the reason that Jupiter and Saturn have very powerful magnetic fields is because they have this dynamo effect happening, rapid rotation, right? And then metallic hydrogen is playing the role of the conducting layer. So instead of the inner core or the outer core of the Earth, the metallic hydrogen is acting like that to generate the magnetic field. Okay? All right, belt and zone circulation. You guys know what that's talking about? The belt and the zone, which one's which? The dark ones are called belts, and the light ones are called zones. Okay, which one's rising, which one's falling? Because it's convection. That's what it is. Okay, so belts and zones are evidence of the convective current in the outer layers, especially Jupiter and Saturn. Uranus and Neptune have them in a limited extent. It's mainly Jupiter and Saturn that show them. Okay, so belts are the descending, zones are the rising. Okay, the book is wrong. Make sure you made it. Okay, but why is it happening? So why are belt and zone circulation part of the story? So Jupiter and Saturn are trying to cool off, right? And the heat energy is trying to escape. The way that it escapes is the most efficient mechanism, right? What's the best way? And it turns out in the outer layer of Jupiter and Saturn, convection is the most efficient mechanism. Now, once it gets to the outside of Jupiter and Saturn, how does it get away from the planet? What process? Radiation. So Jupiter and Saturn are both radiating a lot of heat energy, right? We can't see it. It's not visible light, but it's infrared light coming out of it. All right, what about the Great Red Spot? What is that? It's a big storm, okay? So a big storm has been there for quite a long time, right? Like 500 years. So for 500 years, this thing has been going. How is it possible that the storm has lasted for so long? And so storms represent energy, right? The energy of the storm. Normally, a storm on Earth would get quiet after a while. It would dissipate. But what's going on here in Jupiter? It's being pumped with new energy, right? The energy that's coming out of the planet is giving new energy to the storm and sustaining it, keeping it going. Kind of like, did you go to Griffith? Raise your hand, you went to Griffith, right? There's a big pendulum that swings back and forth. That pendulum should slow down and stop. But what they don't tell you is they give it a little kick. Not to make it move, just to give it a little kick to take away the effect of friction to keep it going. But what's going on? The Great Red Spot should slow down and eventually stop. It's being pumped with new energy from underneath, right, from below. The thermal energy is powering it. Okay. All right. Oblong sphere. It's a word. What does it mean? Stretched out, right? It's not a perfect sphere. It's stretched out a little bit. And why is it stretched out? It's stretched out because it is rapidly rotating. So it's kind of flattening out, but not a whole pancake. It's just a little bit flat. So Jupiter and Saturn are rapidly rotating. You're supposed to know how long they take to make one rotation. Let's review. How long does Jupiter take to make one rotation? 9.5 hours is a good answer. If you're pretty close to that, you got it. You'll recognize it on the test. Okay? What about Saturn? A little bit longer, a little bit shorter? A little bit longer. Give me an answer. Actually, 10.5 hours. So I just sent you the link with the NASA data. It turns out January 18th, I didn't see this. They actually measured the most precise value. It's 10 hours and 33 minutes. I never knew. I thought it was a little bit longer. But anyway, like 10.5 hours, 10 hours and something. Okay. And then what about Uranus? Anybody remember? 16 or 17? Which one was it? I forgot. 17 hours. And then 16 hours for Neptune. Okay, a little bit less. Okay, so Titan. We just mentioned Titan. What's special about Titan? It's the biggest moon of Saturn. The word Titan means huge, right? So what is it? It's the biggest moon of Saturn. We just saw a little video clip where they drop something down. What are you supposed to know about it? It's a big moon. So can you tell me what that means? Do you think it's a sphere? It's a sphere. Why is it a sphere? It's big enough that its gravity can shape it into the form of a sphere. What does that mean, right? Does the gravitational force pretty strong or not so strong compared to other moons? Pretty strong, right? Pretty strong. So the strength of that gravitational field is important because it means that it has the ability to hold on to an atmosphere. The fact that it has an atmosphere, this is special. How many moons have you heard about with atmosphere? Not too many, right? Our moon, no way. But this one does. Why? Well, partly because it's big. It's a pretty big moon. But the most important part is why don't the atmospheric gases escape? And the answer is it's cold, right? So the atmospheric gases are not going fast enough to get away. And so they escape, right? And you don't even know this. The atmosphere is nitrogen, but it has a smog layer with hydrocarbons. You don't have to know that. But it's definitely interesting to think about that. It's like LA smog. Anybody know LA smog? It's not that bad anymore, though. When I was younger, it was more like I lived there one summer, and I'm like, I'm never going there again. I don't want to breathe it. I couldn't breathe. Lung turns like I'm a smoker, 1 pack a day. You know. Anyways, no. Titan. So what I mentioned the big things about Titan. Titan has mountains, lakes, rivers, weather, right? Atmosphere. What are the mountains made of? One more time. Water ice, right? What is the river stuff? The watery, the liquid stuff? Hydrocarbons, ethane and methane, lakes and rivers. We've seen lakes, we've seen rivers, we see deltas. You guys know what a delta is? You don't have to know that, but where the end of a river comes out into a sea or a lake, it spreads, and we see that kind of structure. We see everything. We see winding little rivers. Anyway, you don't need that. Okay. Cassini, I just showed you the pictures. Cassini was a mission. It was only supposed to last for a few years. It left in 1997. It got there in 7 years, right? Did you hear the speaker say why they made it go so fast? So that they would be alive when it got there, right? They didn't want to wait until after their careers were over. And then it was supposed to last nominally 3 years. It lasted for 13 years. Okay, it's pretty phenomenal. I wish I could tell you more. Actually, can I tell you a little bit more? Okay, because the next thing is actually kind of cool too. So there's a moon called Enceladus, right? Who knows what the moon Enceladus is special for? Special. Okay, it's covered with ice, right? Actually, more than that. I feel like maybe we should bring up a picture or two just to show you, because it's kind of special, right? So it's pretty special. Okay, there's Enceladus. Oh man, it is special. Okay, so it's not the largest moon, but what you notice. Okay. What do you notice about it? Do you notice any craters? Mm-hmm. Well, what about those things up there? But they're not craters. There are no craters on Enceladus. None. So what does it mean? No craters. Fresh and new, or old and old? It's fresh and new and brand new, right? It's completely covered with ice. Completely. So you look at those things. Don't they look like craters to you? So what if I told you they're not craters? What are they? Who knows what they are? They are ice volcanoes. They're volcanoes. They're called cryovolcanoes. So what we see happening, and we don't even understand exactly how it's happening, there are jets of water that come shooting out of this moon really fast. So fast that they can get away from the moon. They can escape. And where do they go after that? They go into orbit around Saturn. And they make little tiny crystals of ice that go into orbit around Saturn. And we call this which ring? It's one of the named rings. Okay, you don't know this. Okay, it's called the E ring. Enceladus, E ring. It's a fuzzy ring. It's not a nice sharp ring like the ones that we normally talk about. So this one is outside of those rings. It's outside of the normal zone. But Enceladus is making that ring by shooting this material up into orbit. Some of that may be even falling into the inner rings eventually, but yeah, we'll come back to that. All right, so Enceladus is pretty cool. I'm not going to tell you that. I'm going to tell you that at the end of its mission, Cassini flew 30 miles above the surface of Enceladus. 30 miles. Do you know what that means? 30 miles, it's like nothing. It's like a heartbeat away, right? It flew right through one of these plumes.
No way.
Yes. Because you know what? The scientists have been asking for that from day one. Can we do that, please? You know? And the engineers were like, no way. What would happen if we fly through that and it screws up all of our instrumentation? We'll be ruined. But at the end of the mission, when they were about to run out of fuel, they said, why not? Let's try it. And it flew right through one of the plumes and tasted the water. Isn't that amazing? So it's water, but not just water. Anybody know what else is in there? Organic salt and organic compounds. This is exciting. This is like the soup of life, right? And it's right there, and it's liquid, right? It's underneath the surface. It's really exciting. All right, so yeah, am I telling you how exciting it is? Okay, pretty cool stuff. And then as it ran out of fuel, they made Cassini crash into Saturn so it wouldn't pollute any of the moons, just in case there's life there, right? NASA is considering this as a possibility that there's already life there. And let's not pollute the environment with our spacecraft, okay? So they crashed it into Saturn, so there's no life on Saturn, right? You can't live on a planet like that. As far as I know, I could be totally wrong. I don't even want to tell you what I'm talking about. Okay, so let's forget about that. All right. Yeah, that's a possibility. Okay. Where is it? Okay. Ooh. Okay, so we got that. All right. So the next term, Enceladus, we got that? Enceladus special. So those are the two big moons that you need to know. Titan, it's the moon with an atmosphere, and Enceladus with the jets of water shooting out. That's kind of special. Okay, those are the two ones. There's lots more moons, right? There's 60, how many? 70, 67 moons, but you don't need to know anymore. Okay, those two. Okay. Enceladus, important idea. No, I just said that. Shepherd moons. Shepherd moons, what's that? So this was actually because Cassini went there, it could see little tiny details that we had never seen before. And so one of the rings, called the F ring, we noticed is really thin, and we noticed something strange. It has two little moons, one on either side of it. And they're kind of keeping that ring in shape. So they actually prevent it from straying, right? So they're called shepherd moons. It kind of reconstructs it periodically. So we can actually look at that. Can you look at this? Would this be helpful? I think it would be. Let me just show you. Okay. Okay. So this is the these two moons, right, are one on either side of the ring. And actually we can find it. I have a video. Okay, so it turns out there's probably quite a few separate answers kind of helping you guide your life. Okay, so these little moons apparently are keeping this F ring from this person. So they're kind of keeping it in shape. But they actually modify it every time they go around. You can see it warping because of those moons' gravitational forces. But they are keeping them alive. So actually something about the rings. How many rings are there? There's A, B, C, D, E, F, G, right? So that's how many. Well, that's not right. It turns out there's probably thousands of little ringlets, right? We don't see them. We just count the big letters. There's lots of them. Okay, so actually, you would have seen all of them. So Saturn's E-ring, orbital resonance. What's that mean? Orbital resonance. You mentioned resonance with tidal forces, but orbital resonance says that the moons orbit often with periods that are related to each other. So the innermost one has a period, whatever it happens to be, and the next one out can have a period twice as long or 3 times as long. So we see that quite a lot. The bottoms have resonance, meaning you have periods that are related to the one that's the innermost one. And the reason is that the gravitational force from the innermost one is affecting the other. And so they get into this kind of resonance. So the orbital periods are a multiple of one of the other moons. That's the idea. Okay, so don't worry too much about it. Roche limit is kind of a big deal though. The Roche limit is a concept that if you get too close to a planet, then its gravitational force will pull you apart. What is the name for the force that pulls you apart? Anybody remember that? Called the tidal force. Okay, so here's a moon. Actually, sorry, here's a planet, Saturn, right? And the idea is that the Saturn has a certain radius, R. And this is a mathematical idea. If you go 1, 2.5 radiuses from the planet, so 1, 2.5 radiuses from the planet. This distance from one side to the other is called the Roche limit. So the main rings of Saturn sit perfectly right here in between these points. That's kind of where the idea came from. Okay? The main rings of Saturn are here. The E ring, the fuzzy E ring, is actually outside of that. That's the E ring, right? What creates the E ring again? The little moon called Enceladus, right? That's Enceladus that's making it. But that's outside of the main rings, right? Enceladus. So what about the Roche limit? Does everybody know what the rings of Saturn are made from? The reason we see them so well? What are they made of? They're made of ice, right? So this ice, does it reflect light well? Very well. So does it have a high or low albedo? It has a high albedo. The word albedo meaning reflectivity, right? It has a high albedo. We see it really well because it reflects light like a mirror almost, right? So what about that ice? You see, Saturn, like Jupiter, is still warm from the day it was born. And so it's actually radiating heat energy away from the planet. So what happens when that heat energy hits the little ice crystals? Anybody want to guess? They should sublimate. They should. So are these rings the same rings that Saturn was born with? Not possible. They can't live that long. Now, actually, something came out recently that shows that the rings are also falling into the planet. Don't worry about that part. Worry about the part that they can't possibly be from the beginning of the formation of Saturn because they're made of ice. They should sublimate away. So what does it mean? They're not old. What does it mean? They've been made since Saturn was born. How? Okay, so here's the idea. We got a theory. We got a story. Maybe you're a big lump of something like a Kuiper belt object. Let's say Kuiper belt object. And you decide you want to come visit Saturn. Okay? Hey, Saturn, what's going on, buddy? Oh, not much. And you get just a little bit too close, right? And when I say too close, I mean within the Roche limit. If you remember, these bodies, like asteroids, are not held together very strongly. They're not they never really differentiated. And so what happens when you get inside the Roche limit? They get ripped apart. Ripped apart by what? By the tidal forces, okay? So they get ripped apart. Okay, so what does this story mean? That the reason that Saturn's rings sit just like this is because they've been formed relatively recently. Somebody came too close, probably a Kuiper belt object, made a lot of ice, and then came within the Roche limit. So the Roche limit is the distance at which a loosely held body, like an asteroid or a Kuiper belt object, would be ripped apart by the tidal forces. So can you have moons inside of the Roche limit? Yes, if the moons are well formed, they differentiate close together really strongly. They won't be ripped apart. But these loosely held together bodies like asteroids or Kuiper belt objects would be. Okay, so anyways, that's the idea of the Roche limit. Okay, Saturn E ring, I already mentioned. What's the Saturn E ring? The ring made by Enceladus. How is it made? The jets of water, right, good. Okay, jets of water go into orbit, and there you go. They're in orbit. So the fuzzy little E-ring. Oh, that's a big head. You're watching right now. Sorry about my big head. Okay, can you read this? Okay, so Miranda. Okay, so we're jumping now. We left Saturn, and now we're going to the next big moon, the big planet, Uranus. Right? So a couple of things about Uranus. I have almost nothing. So it's down here. It's down here. But anyway, what's special about Uranus? What do you call Uranus? What do they call it? Ice giant. That's supposed to remind you. Why are they called ice giants? Lots of ice, right? Where's the ice located? In the mantle, right? The same way we have a mantle that's convecting silicate material, the molten silicate. Those two have a mantle made of ice, right? Made of different kinds of ice. Water ice, ammonia ice, methane ice. Maybe even nitrogen ice and oxygen ice. I don't know exactly what's inside there. But the ices are definitely there. Okay, so I only have one moon for Uranus. Its name is Miranda. And I have one moon for Neptune. Its name is Triton. Okay, so you need to know those, right? Miranda's a pretty funky moon. If you saw the pictures of it, actually it's on Bill talked about it, right? All right. So what did he talk about? What was special about it? What do you remember? It's a pretty strange looking moon, right? It's got a weird personality. If you look actually at one side of it, this one side looks very different than the other side, right? And actually, when you analyze the material, this side is made of one kind of material, and this side is completely different. So what happened? Okay, two small moons smashed together, but not too hard, and they welded together to form Miranda. That's what you're supposed to know. It's pretty weird looking. Because of the weird structure that it has, it turns out there's a cliff on this moon. It's the tallest cliff in the whole solar system, right? It's one of the tallest cliffs in the whole system. Verona Rupa, right? Whatever. I don't think you need to know that. But mainly, it's just interesting. Strange looking moon. It's two small moons that got welded together when they collided, right? So there's one. And the same guy. We said retrograde orbit. Who knows what that means? Retrograde orbit. Going the wrong way. Okay, so if a planet is born in our solar system, right, what we expect to see is that the planet goes around the sun in the same direction that we go around the sun. We expect the planet to rotate in the same direction. We expect any of its moons that are born with it to go in the same direction. What is the explanation? Conservation of angular momentum, right? So what happens when we look at a planet like Saturn or like Neptune, and we see a moon going the other way? What do you immediately say? Was it born with the planet? It was not, right? There's no way. It came from somewhere else, okay? So it not only is going the wrong way, that's called a retrograde orbit, it has a highly elliptical orbit. So does anybody tell me what happened? Where did it come from? It was captured, okay? So that's the idea. It's elliptical, it's going the wrong direction. This moon wasn't born here, it was captured. And where it was captured from is probably, that's one of the things you have to know, from the Kuiper Belt. So we think this is Triton we're talking about, with its retrograde orbit, highly elliptical orbit, is a Kuiper Belt object. And it also has some interesting features, okay? So what's interesting about Triton? It has a very weak atmosphere, much, much less than Titan. Often people get confused, Triton, right? Titan is around Saturn, has a very thick atmosphere. Triton is around Neptune, and it has a very tenuous atmosphere. It has a little bit. But it also has cryovolcanoes. What does that mean? They're not lava volcanoes, they're cold volcanoes. And what do? They erupt not with water, but with liquid nitrogen. So that's what you're supposed to know. Liquid nitrogen spewing out of the inside of the planet, which means that it has underground reservoirs of liquid nitrogen. How about that? Does anybody know about liquid nitrogen? Really hot or really cold? Really cold stuff, right? We're really cold out here. But it manages to be warm enough to be shot out of, like a cannon almost, out of these volcanoes. So Triton, moon of Neptune. Okay? All right, so moving down, here we go. Some of the described things I'm going to be able to. How does the sunlight intensity change as you move away from the sun? 1 over the distance squared, right? So the easy thing to do is just talk about all the planets that we talk about, right? How about Jupiter compared to the Earth? How far away is Jupiter from the sun? 5 AU. That's 5 times as far away as Earth. So what happens to sunlight if you go 5 times as far? It's 1/25, right? 1 over 5 squared. What about Saturn? How far away is Saturn from the sun? 10 AU. The numbers are kind of easy. We use the easy version, right? If it's 10 AUs, what's the intensity of the sunlight? 1 over 100, right? 1 over 10 squared. Uranus, about 20 AUs. What's the intensity? 1 over 20 squared, or 1 over 400. And Neptune's about 30 AUs. What's the intensity of the sunlight? 1 over 30 squared, 1 over 900. Okay, that's the intensity of the sun. Okay. Describe how Io, or Io, is the most volcanic body in the solar system. What makes it so volcanic? It's right next to Jupiter, right? And so what's going on? How did it get so hot? It should be cool already. It's a little tiny body. It's a little moon. It should be cold. But because it's so close to Jupiter, what's going on? What is giving it new heat energy? There it is. Yeah, come on, you know. It's right next to Jupiter. So the same force that we talked about before, which is the Roche Limit, the tidal force, stretching it, right? Like putty, like taffy. And as you stretch it, it gets hotter. Okay? And it gets hot enough to actually begin erupting. And it's really erupting. And at any one time, it can have like 300 volcanoes. Okay? How is the ring structure of Saturn so special? So anybody think it's special? I think it's special. It is incredibly special. Unbelievable. First of all, how big it is, right? It's huge. How big is it? It would actually fit in between the Earth and the Moon. It would just about, it would fit fine, actually. It would fit, it's about that distance, though. It's almost 300,000 kilometers, right? That's pretty crazy. It's that wide, but then how thick it is. That's the part that's crazy. How thick is it? 10 meters, the width of this classroom. Imagine anything the size of a planet being that skinny. Isn't that all you're, okay, it's like razor thin. Yeah, okay, I know, you're getting ready for tomorrow. Okay, so that's the big deal, right? So why are they so visible? So we got that. Everybody got it? So big, 300,000 kilometers and 10 meters thick. That's amazing, right? How skinny it is. So what made it go that? Why is it that thin? What makes it that thin? Anybody tell me, why is it so skinny? You're in a region where the gravitational field is strong, right? And remember that when you have conservation of angular momentum, because it's the same process, right? It flattens it into a pancake. But that force is so strong, it really thins it out, right? So these objects just got squished into a thin little pancake from conservation of angular momentum and the strength of the gravitational force. Right? They're really close to the planet. So why are they so reflective, so visible? They're made of ice. Okay. How about the other ones? Why are Jupiter, Uranus, and Neptune so hard to see? They're not made of ice. What are they made of? Mostly rocky, dark materials, carbonaceous maybe, but they're not very visible. So they have a high or low albedo. You sound good, right? I sound intelligent. They have low albedo. Can't see them. Okay. They don't reflect light. That kind of thing. Okay, why is Titan so special? I've already talked about it a couple times, but what are the key things that you remember? Titan, special because atmosphere, number one, right? Which means it has weather, but it also has mountains and lakes and rivers and rain and everything that you would imagine is kind of Earth-like. Except the alien part is what they're made of, right? They're not made of the same stuff. So what are they made of? One last time. Water, ice, mountains, lakes and rivers made of ethane, methane, organic compounds. Okay. Jump down. Why does Uranus have the most extreme season? Okay, we didn't talk about it before, but now we can talk about it, right? What about Uranus you're supposed to know? You're supposed to know that Uranus is tilted over on its side. Okay, so what's the tilt of the Earth? 23.5 degrees, but for Uranus it's what? 98 degrees or something, right? It's like literally on its side. So what does it mean? Does it have seasons? Yes, it has seasons, but sometimes it's pointed at the sun, and then the other side is completely pointed away from the sun. It has extreme seasons. Okay, the other thing you're supposed to know, and I think I talked about it just down a little bit lower, is how long does Uranus take to go once around the sun? 84 years. If you don't remember that, maybe write it down to help remind you. How many people are 21 years old? Right? You get to drink. Well, guess what? That's one season on Uranus. Okay, that's one season. So 21 years is 1/4 of the cycle. Each season of Uranus is 21 years, and they're very extreme. Okay? So we see on Uranus and Neptune, we do see seasonal effects where on the surface, there's no surface. That was a trick question, right? There's no surface. They're giants, right? But we see it in the atmosphere. We see clouds forming and, kind of more clouds in the wintertime, less clouds in the summertime, that kind of thing. Okay, what's strange about the ice giants' magnetic field? I alluded to this in class the other day, but if you didn't hear me, what's not weird about Jupiter and Saturn's magnetic field? Let's start with that. They're lined up with the axis of rotation. They're really well lined up. But what's strange is the axis of rotation and the magnetic field are not lined up with both Uranus and Neptune. Let's see a picture of that. Okay. So if you ask me why, I'm going to tell you I don't know. Because I don't really know. But the Uranus and Neptune both have strange magnetic field. Where is the magnetic field? Oh, it's way back here. Okay, so you can see, and happened before. Okay, come on. All right. So you can see that the axis of rotation and the magnetic field are great for Jupiter and Saturn, but they're all a kilter. They don't work. Something weird. So is this, first of all, do they have metallic hydrogen? No metallic hydrogen. Why not? Why don't they? They have hydrogen. Why don't they have metallic hydrogen? There's not enough pressure. Why isn't there enough pressure? There's not enough mass to give them the gravitational force to make the pressure. So they're just not big enough. Okay. If they were bigger, would they have metallic hydrogen? If they were bigger, they would have metallic hydrogen too. But they're not big enough. Okay. So, anyways, what causes their magnetic fields? And the answer is something else, right? Some other kind of currents, probably in that or near the convective mantle, but I don't know. And you don't have to worry about it anymore. Okay? So just weird, right? That's what's weird about it. Okay. That's what's weird. Review. Reset. I don't know why what about all right. Next thing up. Okay, chapter 8, and next one. Okay, describe what is unusual about Titan and where you're probably originating. Hopefully by now you know the answer to that question. What is the answer? What's weird? Retrograde orbit, number one, right? Retrograde orbit, very unusual. So where did it come from? They were captured, right? How many force surfaces is that? Oh, that one.
Thank you.
So, what is unusual about Titan? It probably comes from the chemical belt. Okay, chemical made of nitrogen bodies, lots of nitrogen. Minerals, the poor guy in the news, I know the robot again in Callisto. You got that? The rotation rate and the size of the giant. Let's go through that again. Rotation rate. What's the rotation rate of Jupiter? 9.5 hours. Saturn, 10.5 hours. Uranus, 17. Neptune, 16. Something like that. How about the sizes? How big is Jupiter compared to the Earth? 11 times as big as the Earth. Saturn, 9 times. Uranus and Neptune, 4 times. Okay. And orbital periods. Oh, you got to remember that. How long does Jupiter take to make one revolution around the sun? 12 years, about 12 years. Okay, just get the rough idea. Good enough. Saturn, 30, 29, or 30 years, close enough. Uranus, we just mentioned a second ago, 84, 4 times 21, right? Remember 21. And then Neptune, 165 years. Okay, something like that. Okay? And that will be useful at some point. Okay, so now go back to chapter 5. Chapter 5, okay. Chapter 7, oh, we're going backwards. Reverse order. That's fine. Okay, chapter 7. All right, chapter 7. Chapter 7. Okay. Chapter 7. Chapter 7. Okay, can you guys read it? Okay, start off with the terms. Differentiation. So by the way, what are these things? Differentiation, cooling, cratering, magma flooding, weathering. What are they? The 5 stages of terrestrial planet formation. So you need to know those, right? That's what they are, the 5 stages, right? So what does each one mean? Differentiation. So you start off, you gathered together a bunch of material. It took a while. You were a protoplanet, and then you started gathering more material. Now you're a full-fledged planet. You've gathered all this material together. Inevitably, because you pulled it from far away, what had to happen when you pulled it all together? It had to be really hot. In fact, molten hot. If you're molten hot, then this can happen. Differentiation. What does differentiation mean? To separate by the densities, right? Separate by density. So the denser layers are where? Down, right? They sink. And the lighter, less dense, they float. Okay? So the innermost density is always the highest, the outer one is always the lowest. And then cooling, that happens to everybody. Everybody starts to cool. What happens when you cool? You cool and form a crust, right? You form the crust first. Now that you've got a crust, you can mess it up. And so the cratering is the evidence of impact events. And so we talk about how everybody's got a crust and everybody has craters. Well, not everybody, right? If you have craters, that surface is old, representing the cratering that's taken place in your lifetime. If you don't have your craters anymore, then you can deduce that something happened to resurface that planet, that object, right? So lots of craters, old, no craters, new, right? That's what we say. And you can even you can date how old the surface is by the number of craters. Magma flooding, what is that? Get hit pretty hard with an impact event. It can actually crack open your crust and allow the magma not to explosively come out, but to just flood out, come out of the crack and fill in any holes in the ground, like valleys or craters that are there. So if we look at our moon, it's like a really perfect example. So what is an example of magma flooding on the moon? Where do we see that? The Maria, right? The dark areas of the moon that are flat and there's no craters there. What had happened is the magma came up through the crack and filled in any valleys and craters that were there. So those used to be the deepest valleys on the moon, and then they got erased by the magma flooding up the cracks. Hey, weathering always takes place on a terrestrial planet, right? Only if there is an atmosphere. So does it happen on every terrestrial planet? No. If there's no atmosphere, there's no weathering. Okay? Because you can't get weathering unless you've got an atmosphere. So of all the terrestrial planets, there's 4 of them. Which one does not have any weathering? Mercury. What does it mean? Nothing gets. Oh, that's not. Okay, never mind. This is review. Never mind. Okay. It turns out that never mind. I know. There's just so many details, right? Yeah. So those cratering things can actually do. Never mind. Okay. But yeah, no weathering. Never mind. Okay, stop. Okay. So Mercury, old, no weathering. Okay. But every other planet we see. What's weathering mean? Somebody was confused about this. What does it mean? The mountains get smaller, right? There's mountains are getting smaller. They're getting worn away by weathering. It's the wind and the rain. It can be wind or rain or both. It can be freezing. It can be all kinds of effects like that. Wrinkle Ridge. What are we talking about in particular? Mercury, right? That's one of the cool things about Mercury. We see that the crust formed and then the core shrunk. And as a result, what happened is the extra crust had to wrinkle. So that's a Wrinkle Ridge. The technical name is not up there, so I guess you don't really have to know it. Anybody know what it is anyways? Low-base scarp, okay, which means cliff, right? Low-base scarp. Okay, so Wrinkle Ridge, we're talking about Mercury in particular, but we find them on other bodies as well. Any body that formed the skin and then the core shrunk is going to make these wrinkle ridges. Okay. Fossil magnetism, what does that mean? Trace amounts of magnetism. We can see trace amounts of magnetism, but there's no active dynamo effect on that body. Right? So Mercury, fossil magnetism, and also Mars, very weak magnetic field, mainly fossil magnetism. Okay, so it's just left over. It's been ingrained in the crust materials itself. Think about it like that. Tidal synchronization. What does this mean? Tidal synchronization. The tidal force causes the orbital period and the rotational period to synchronize, right? So we see this exactly in our moon, right? What is the orbital resonance of our moon? Is it tidally synchronized? Is it tidally locked? Our moon is tidally locked. It's a one-to-one orbit rotation resonance, we call it. But when you look at Mercury, we see it's a little bit different. Does everybody remember that? Mercury goes 2 times around the sun and rotates 3 times in the 2 years that it goes around the sun. 88 days to go once around the sun, and it takes 59 days to make 1 rotation. So Mercury has a 3-to-2 orbital resonance. That's what it's called. Okay, and we see it a lot. It's actually a very common thing to see. Okay, retrograde rotation. What planet are we talking about? We're talking about the one that flipped over and now it's rotating backwards. What is it? Venus. That's Venus we're talking about. So Venus has an incredibly slow rotation rate. By the way, the slide was wrong. So if you're in my 8 a.m. class, I'm embarrassed to tell you. The tutor came in and said, that number's wrong. I got served. I like that. That was good. So by the way, let me tell you the right number. Now that you're here. Glad you're here. Venus takes 225 days to go once around the sun. That's the year. And it takes 243 days to make 1 rotation. Venus is weird. And it's rotating the wrong way. Okay, so it's rotating the wrong way. It goes the right way around the sun, but something must have hit it to knock it upside down and make it rotate in that opposite direction. Okay? So caldera, who knows what that is? Caldera. Caldera? Geology people? Caldera? Yeah, volcanoes, right? A volcano erupts and then kind of finishes erupting and seals up. And then where it's sealed up, it starts to sink. That's called a caldera. Why is it sinking? Because the magma has receded. And so I'm actually referring to Venus. This is a Venus idea. I think maybe I take the word out. Oh, there it is, corona. You guys see the word corona? That's not the beer. It's not the sun. Corona, okay? On Venus. Let's talk about the corona on Venus. Okay, corona on Venus. Does Venus have active volcanoes right now? No active volcanoes, but we think Venus is incredibly volcanic. So what happens in the world, right? Actually, we see it on Earth too. Actually, it's kind of like a pimple. Sorry, I don't want to talk about pimples, but imagine you have a pimple. Okay, sorry. Yeah, okay. It's a really good analogy. Okay. Venus is really flat, by the way. There's no big mountains on Venus. Okay, but there's this pimple. It's about to pop. Sorry, gross. But what it is an upwelling of magma, right? This is a magma pimple. I'm not sure if this is a good idea or not. Anyways, okay. And then it naturally pops. Don't squeeze it, right? I'm sorry. Okay, so what happens is it comes out. This is gross. Okay. And because it's so flat, it ends up going a pretty good distance. And so what we see when we look down at Venus is we see these circular rings that are actually flooding of magma around this little point right here where the pimple was, okay, where the magma was. Okay? And then what happens is the magma recedes. It goes back. It goes back to where it came from. And so now that it's not there pushing, it turns out this thing ends up sinking down into the ground. What does it look like when you're done? It looks like a crater, actually. It looks like a crater, but it's not a crater. We call it a caldera, or this whole thing right here with a caldera in the middle is called a corona. Okay, a crown, corona. So this is a feature we see on Venus, and this can be almost like 20 miles, or what would 20 miles be? 30 kilometers, right? 20 miles, 30 kilometers in size. They're pretty big. But anyways, the reason they're so big is it's so flat, the magma can flow easily in any direction. And they're circular because it's flat, right? Because they flow in every direction away from the center. Okay, but when they're finished, they sink back into the ground. This is what a caldera does, okay? So this could be caldera. And we see this on Earth in dormant volcanoes. After they erupt and they cap off, they sink back down. So the inside, the caldera is at the top of the volcano. Sometimes there's a lake there, right? And actually that caldera, yeah, there's the lake. All right, done. Olympus Mons. What's special about Olympus Mons? Where do you find that? Mars. We're talking about Mars right now. Olympus Mons. Why is it special? The tallest volcano in the solar system. Okay, you should know that. And then you should know why it's the tallest volcano in the solar system, right? What's special about Mars that made it possible to grow a big volcano like that? So was volcanism important for Mars at some point? It was, right? Definitely volcanoes. By the way, the atmosphere, carbon dioxide, volcanoes, right? Volcanic activity emits carbon dioxide. There are no active volcanoes because Mars is pretty cold now. But once upon a time, it was hot, and this volcano erupted, right? So what's it called when you have a volcano forming? The process is one of those plate tectonic kind of ideas. A hot spot. Remember hot spot? Okay, so there was a hot spot. There was a thin part of the crust. The magma was leaking out from the inside of Mars and making this volcano. Now, did the hot spot move? No, it did not. The plate didn't move. And in fact, we think that there's just one big plate for Mars. Okay, but the fact is that this thing is huge, right? It's taller than Mount Everest, much bigger than that, actually. How did it get so big? Well, it just grew year after year after year. If we took this volcano and put it on Earth, what would happen? It would actually sink back down into the Earth. The crust is not strong enough on Earth to support it. So what does it tell us about the Martian crust? Much thicker, right? So we know from this volcano, just that, we know that Mars was volcanic, right? We know that it had a hot spot, but it didn't move, right? That the plate didn't move. And the crust of Mars is really thick to support such a large volcano. Okay, so we learned a lot from that. And then the other big feature is Valles Marineris, right? And that is what? This giant, Rift Valley. How did it form? No idea. Okay, no idea. It's huge. 3,000 miles long, 100 miles wide. It's a big scar across Mars. Okay, I don't know why I keep putting these on here, but I did. Blueberries, what's a blueberry? Is it an actual blueberry? No, actually, so I left it in because it's like old school. See, once upon a time, we weren't sure. Was there water on Mars? Maybe. And now we're like, forget about it, right? There was so much water on Mars. You're supposed to know, by the way, I don't know if I have it in there. If I don't, you guys are here. You're supposed to know that NASA made a big announcement in the spring, in April 2018. Does anybody know what they said? Two big things, right? There's water, liquid water, reservoirs, lakes underneath the surface. You should know that, right? Mars has right now liquid water lakes underground. And then I think there's another cool thing you should know. They detected something in the atmosphere. Methane gas that was seasonal, right? It means there's more in the summer and less in the winter. And I told you what that means. There's life on Mars. I know I can't say that for sure. Question, comment? How much liquid? This is a significant size lake. How much water is on Mars? We think that there's probably almost 80% of the original water there. So even though it lost a lot of water, it kept a lot of water too underground, right? Still there. So we don't know for sure, but that's our estimate right now. Okay, and most of it is frozen. Most of it is frozen underground, but there is also these liquid water reservoirs. Okay, Noachian. There's actually pre-Noachian, Hesperian, Amazonian. They're in correct order, right? Which one was the good time on Mars? Noachian, right? That was like when Mars had a magnetic field. It had liquid water at the surface. It had an atmosphere. You could imagine life there. It had a greenhouse effect that you could imagine. Hesperian was after this, as the magnetic field is decaying, so it's not looking so good. And now that's today, Amazonian. So I don't know what you need to know about Hesperian. Maybe just that the magnetic field is starting to go away. You remember the stages that Mars became cold and dry, right? How did it happen? You were supposed to know that, right? So Mars was great, wonderful place, and then what happened? The core cooled, right? And when the core cooled, it lost its magnetic field. Now there's no magnetic field to deflect the solar wind, so the solar wind blows the atmosphere away. Now you don't have an atmosphere. What happens? The water has to evaporate because there's no pressure. There's not enough pressure to keep it in the water form. And so you don't have the water, you lose all that, and basically you end up with this cold, dry world. No greenhouse effect anymore, no water to surface, cold, dry planet. Okay, any questions? All right, you got the terms. Let's look at the hard thing. Okay. Okay, so I think I told you already. What are some of the features of Mercury's surface? Anything? Wrinkle ridges. Okay, wrinkle ridges. That's a good one. There's also a big Polaris basin, wrinkle ridges, and that's NASA. Right? NASA announced they saw a new wrinkle ridge that wasn't there before. So that means what? What does it tell you that a new wrinkle ridge forms? It's still cooling down. The core is still shrinking. Even all this time later, it's still shrinking. Okay. How does Mercury have a little bit of hydrogen and helium at the surface, but not have an atmosphere? These are ideas that I think you should know. It's captured temporarily some of the solar wind. The solar wind is made of hydrogen and helium, not the full atoms, by the way. They're made of the nuclei of hydrogen, nuclei of helium, and electrons. Right. That's the solar wind blowing out. But then Mercury captures them, and I don't know that they've really detected hydrogen and helium, or maybe just the nuclei. I think they would have to. Never mind. Okay, I know my answer. Never mind. They've detected the full atom spectroscopy. So that means they must have captured electrons to become atoms again. But it's temporary. Okay, what are the differences and similarities? That's a huge question. Should we try to break it down a little bit? Okay, number one, let's say structure, right? Let's try similarities first. Okay, similarities for 2000. What are some of the similarities between the terrestrial planets? Yeah, they all have cores and mantles and crust. Okay, core, mantle, crust. They all fit that. That means they all underwent differentiation. That's the process of differentiation. So all the terrestrial planets were hot when they started. They were molten when they started. These are all similarities as well, right? You think back, how do you get differentiation? You had to be a big molten body. And they have their iron nickel cores, they have mantles of silicates, they have crust. Okay, anything else? Do they all have atmospheres? No, Mercury, darn it. Okay. The other three do, but not Mercury. Okay, so that's, what else is similar then? They all have moons. Oh, no, that doesn't work. Who's got moons? Earth and Mars, okay? Venus, no. Mercury, no. Okay. I don't know. What else is similar? What is it? Close to the sun. They're relatively close to the sun. The terrestrial planets are less than 2 AUs from the sun, right? So they're inside of the asteroid belt. They're pretty close. The giants start at 5 AUs. So we're less than half that distance, all of us, right? All of the terrestrial planets, relatively close. So because it's so close, what does it mean? Pretty warm, pretty cool? Pretty warm, right? It's pretty warm, close to the sun. We get a lot of solar radiation, okay? So solar radiation is more important for the inner planets than it is for the outer planets, right? I don't know. I can't think of too many more. Those are pretty good. How about some differences? Are they all alive? No? Well, okay. Technically, yeah, I know. Define alive. How do you define alive? What does it mean to be alive? You're a planet. You're alive. There's something going on, right? The surface is changing somehow through some mechanism. There's some kind of mechanism for changing. So you still have some heat usually inside, or else you can't do that. If you don't have any heat, you're cold and dead, then nothing's happening. You are dead, right? So is Mars alive? Let me go backwards. Mars? Yeah, it has atmosphere still. So it's warm enough to still have an atmosphere. If it gets much colder, then it probably will lose that atmosphere. Right? But Earth, we know, is alive. How about Venus? Alive? Very much alive. Really hot on the surface, right? Those are some of the things that I didn't put it down there to memorize. But you are supposed to know what the atmosphere of Venus is made of. Who knows what it's made of? Anybody? Carbon dioxide. Okay, carbon dioxide. Pure carbon dioxide. You're supposed to know the clouds are made of what? Sulfuric acid. I don't know why it's not on the study guide. It should be there. Sorry. You're supposed to know it anyway. I have a question on the test about that. So the clouds are made of sulfuric acid. Does it rain on Venus? Sure. Does the rain hit the ground? Never, right? It's too hot. So you need to know it's really hot. And how often does the sun shine on the surface of Venus? Never, right? Never. It's completely covered with clouds. So you never see the sun hitting the ground. All right, let's see. Okay, why does Mercury, Venus, and Mars not have strong magnetic fields? Let's start with Mercury. How about Mercury? It's too cold, right? So no molten metal, right? No molten metal. It's still rotating, right? Pretty slowly, but better than Venus. But there's no molten metal anyway, so there's no magnetic field. The fossil magnetism that we talked about. How about Venus? Venus. It's hot, so it's got molten metal, but it's really slow rotation. Remember we said a second ago, 243 days to make one rotation. It's just so slow. That's how it lost its atmosphere in the first place, right? Okay, so blah, 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 evidence. What's the evidence for Mars being a wet world? Now you have so much. But give me one bit of evidence. Anything you want. Yeah. Sedimentary rock. That's great. That's cool. How about the recent news from NASA? Hey, NASA says there are liquid water lakes underground. That's pretty good. Okay, yeah. Anybody else? Oh, cool. Besides sedimentary rocks, there were another little tasty little fruit. Blueberries, right? The little blueberries are hematite crystals, and they can only form in liquid water environments. Okay. Let's see. So, blah, blah, blah. I think we talked about some of these, right? How does Mars have the largest volcano? Everybody good? You know why? What's the answer? Thick crust, right? And hotspot moved or didn't? The plate didn't move. The hotspot was in one location, just kept feeding the tube to build this big volcano. How do we observe seasons on Mars? First of all, does Mars have seasons? Why does Mars have seasons? Because it's tilted. And if you remember, it's tilted 25 degrees, which is remarkably close to the Earth, right? But how do we see the seasons on Earth? I mean, on Mars, sorry, on Mars. We see the poles, right? The ice builds up at the pole in the winter or the summer. In the winter, the Martian winter, you see ice build up at the pole. Oh, wait a second. What kind of ice? Carbon dioxide ice, not water ice. Okay, where's the carbon dioxide coming from? From the atmosphere. It's cold enough in the winter that the gas turns right into a solid and deposits at the pole. So we see the pole ice, and then it goes away. In the summer, it's gone. Right? Winter, it's there. Describe the sunset on Mars. Do you guys know what I'm talking about? Did you see it? Oh my God. Did I forget to do that? Oh, man. What does the sunset on Mars look like? Oh, wow. Good thing you're here. Oh, that's so beautiful. So the rovers on Mars have been watching the sunset for years. Okay, and there it is. The sunset on Mars is blue. Okay, write that down if you're going to know that. The sunset on Mars is blue. Okay, so that's kind of weird. And it kind of gets into a little discussion. You know why the sky is blue? But what happens is when the Earth atmosphere is really small, and they scatter short wavelength blue light. And when the sun is setting, what does the sun turn? Orange, red, white. And the reason is the sunlight has to pass through more and more atmosphere as the sun gets older. And so all of the short wavelength gets scattered, and only the longest wavelength light, the red, makes it all the way through. The sunsets on Earth are red because the atmosphere gets rid of the other colors. So now, go to Mars. What color is the sky on Mars? It's red. You know how I know that? I've seen it with a telescope. And when we look at the Earth from another place, what does the Earth look like? Blue, right? The Earth is blue because that light is scattering in every direction. So Mars scatters red longer wavelength means what? The particles in the Martian atmosphere are larger. They're larger particles. That means they shine a longer wavelength light. When the sun is setting on Mars, all of the longer wavelengths go away, but the short ones stay through this spot. So the sunset. Got it? It's pretty cool, right?
Does scatter mean reflect in other directions?
It means absorb and don't worry too much. Yeah, just say Saturn. It's called Radial Saturn. Okay. Okay, so I just described sunset on Mars. Okay, explain why all of the terrestrial planets began with CO2 atmospheres, and how Earth's atmosphere became nitrogen and oxygen. So, what do you call CO2? CO2 is called a primary atmosphere. Primary atmosphere. That means you start with that. Why do we always start with CO2? What makes the CO2? Volcanoes, right? So every one of the terrestrial planets had volcanoes in the beginning, at least. And then little by little, as they cool, they lose those volcanoes. And Earth still has a couple, right? A few once in a while. And Mars, no. Venus lost lots of volcanic activity. So CO2 is always part of the first atmosphere. But then what happened on Earth is a little bit different. Is life began, right? And life is something special. It used the CO2 to build its own structure. I don't know if you know how plants grow. Does anybody know? How do plants grow? Did they take the nutrients out of the soil and use those? They use the air, right? They suck stuff out of the air. They suck carbon dioxide and water out of the air and out from the watering. And they turn it into carbohydrates, right? Into long chains of molecules to build the structure. Okay, I'm getting off on the tangent. Anyway, life takes the CO2 and uses it in its structure. So things like shells of sea creatures, right? They're made of calcium carbonate, which has CO2 in it. And then they die, and what happens? It settles down to the floor of the ocean. And so year after year, it's like sedimentary rock forming. You get year after year of these calcium carbonate containing minerals, and they eventually turn into rock. Okay? So where's the CO2 on Earth? It's in rocks, right? It's underground. It's in mountains. It's there, but it's not in the atmosphere anymore. It's locked into the rock. Okay, most of it, into the dead light, things that were alive ones have trapped it. But what did they leave behind? They left behind the nitrogen and they make the oxygen, right? That's where we get it from life. So the other planets didn't get it because they didn't have as much living stuff. Clearly, maybe Mars had a little, we just don't know. Okay. And then the last one, the order of events which led to Mars becoming a dry and nearly dead world. So I think we've done it already a couple times. One last time. Stage one, core cooled. What happened as a result of that? Lost the magnetic field. Magnetic field's gone now. The solar wind blows away the atmosphere. No atmosphere, no pressure. The water evaporates. Now you've got no water. The water's gone. You have a dry, cold world. Okay, no greenhouse effect. What are the 5 stages of the evolution of a terrestrial planet? You want to try? Number 1, before cooling, differentiation. You're a hot, molten body, and you separate by your density layers. Differentiation. Next one, cooling, making a skin. Now that you've got a skin, you can mess it up. Cratering, right? Some of the cratering events are going to be powerful and crack open your surface and allow the magma to leak up. What's that called? Magma flooding. And the final stage, weathering. Final stage, weathering. Okay. The tilt of Venus, 180 degrees, right? Retrograde rotation. Tilt of Mars, 25 degrees. And the rotation rate, 24 hours and 37 minutes, something like that. A little more than 24 hours. Okay? Okay, everybody good? Chapter 7? Okay. So, Danny, we're going backwards. Yeah, we'll come back to it. So, let's see. Chapter 6. the last chapter? Okay. Oh, there's. Holy mackerel, there's a lot. Boy, I can remember all this stuff. Good question. Okay. So lots of words. Again, let's try to. You guys want? Am I going too slow? Raise your hand. Slow. Go faster. Too fast. Too fast. Slow. All right. So radioactive decay. Pretty important. Why is it so important on Earth for radioactive decay? It's one of the key parts for keeping the core hot. Okay. What does it mean? Because actually, there's a question on this. Okay? So actually, there's questions on lots of stuff up here, right? This is what you focus on. Radioactive decay. What does it mean? What's radioactive mean? Okay, I'm looking for the word unstable. Right? Unstable. That atom that's radioactive cannot stay that way. It has to change into something more stable. So it's called the parent and the daughter isotope. Okay? So anyways, what it turns into is more stable than what it was when it started. Okay, that's radioactive decay. There's a half-life. You got to know about half-life. There's a question. I think I gave it to you ahead of time. You have some of you. If we'll do the 10 questions in a few minutes, and then you can see that's one of the questions. Okay? So half-life means what? The time it takes for half of a radioactive substance to decay, turn into a more stable element. Okay, the core, mantle, lithosphere, crust. Those are what? The layers of the Earth, right? So where's the core? In the middle. Is it just one piece? No, there's two pieces. What are they called? The solid inner core and the molten outer core. What are they made of? Iron and nickel, right? Iron and nickel. Okay. Mantle is the layer outside of that. The next layer outside of the core. What is it made of? Okay, the answer is silicates or magma, right? It's made of rock. Molten rock that flows very slowly in convection patterns, right? And then finally, at the upper part of the mantle and the boundary with the crust, we have this thing called lithosphere, solid rock. Okay? At the base of the crust, the top of the mantle, we have solid rock. And then the crust. And the crust is floating on top of the mantle, right? Mostly, yeah. And the reason is what? The crust is more or less dense than the mantle. Okay, so it's on average less dense, but is all the crust less dense than the mantle? And the idea is no, right? Yeah, you're showing me subduction, right? Okay. But what kind of crust is more dense and which kind of crust is less dense? I know it's coming up in a second. Okay, more dense. Oceanic crust, more dense. Made of what? Basaltic material. And the less dense, the continental crust, is made of granite. Okay, this is a less dense form. Granite and basalt are both SiO2, silicate. They're both silicate. But one of them has big crystals and one of them has small crystals. That makes it less dense and more dense. So granite, big crystals in it. That's why it's so pretty, right? And basaltic, not so pretty, very tiny crystals, almost none. Okay. All right, so basalts, we just said basalt. What's another name for a basalt? Solid lava, right? Lava came out of the ground, solidified, that's a basalt right there. So if you've seen pictures of lava flows near a volcano, those are basaltic materials. Now, can we find them in other places? Of course. Did you know that they're right near Santa Barbara? Anybody? You can find basaltic materials just up the coast a little ways, right? Former volcanoes, right here, like crazy. Anyway, okay. Seismic wave. What is a seismic wave? Earthquake, right? And there are two kinds. You have to know that. You have to know that they're called P and S, right? So who knows why they're called P and S? Primary and secondary. So primary gets there first, right? So they're not the same speed. P waves are faster than S waves. And then you also need to know a little bit more. P waves are pressure waves. What can they travel through? Solid, liquid, gas. Yeah, everything, right? Pressure waves can go through everything. Can they go through the molten mantle? Yeah. Can they go through the mantle actually propagates gas waves too. They can go through the molten outer core as well. but S waves cannot. S waves don't go through the outer mantle. They can't be propagated. So those are shear waves. Heat transfer, convection, radiation. You're supposed to know what those are. Convection means what? Two things are touching. One of them is hot, one of them is cold. Which way does the heat flow? From the hot into the cold. Okay, that's called conduction. You have to be touching. The next one is called convection. What's happening there? A hot and cold are separated from one another, right? And so the heat flows between them with a convective fluid. And so in the mantle material is flowing. That is convection, right? And also, if we go to the Earth, the surface of the Earth, the crust of the Earth heats up the air, and in the atmosphere we see convective coils of air, right? The air will take the heat energy from the ground and take it up to the clouds. That's also convection. And then the last one, radiation. What is radiation? It means we're referring to light. Light. So light is emanated by things that are hot. The hotter they are, the brighter the light will be, and the color changes as a result. So what about the Earth and you and me? What kind of light do we radiate? In what range? The infrared. Right? We all radiate infrared. You are radiating with light. You know that. I showed you the pictures. Right? You forgot they're on canvas. Okay. There's a picture of you on canvas in infrared. Okay. So just so you know. Shield volcano. Oh, plume. Sorry, plume. We know it's a plume. Did I really put that in there? Who knows what a plume is? I forgot to put that in. A plume is in the mantle. It's a movement of material inside the mantle. A plume. Okay. And so as it rises, it pushes on the tectonic plates. So actually, it's a pretty good word to put in there. Why do the tectonic plates move? The answer is forces from below, from the mantle. They're pushing on. They're not moving very fast. It's really a slow creep. But the plume is probably a good explanation, right? The plume pushes on the tectonic plate. What's a shield volcano? It's a regular kind of volcano. What happens? There's a place where the magma comes up, it erupts, and then comes down and forms a cone shape. We call it a shield volcano. Where do you see that? Hawaii is a great example. I've never been there, but I hear it looks cool. Okay. Is it nice? Really nice. I want to go. Okay, so we've got plate tectonics. There are 5 things you're supposed to know in plate tectonics. Hotspot, continental collision, subduction, spreading center, and transform fault. Okay, so those are all up there, 5 different things. You should know what they are, but also where they're happening on Earth, right? So where is, what's a continental collision mean? What's happening? 2 continental plates are smashing into each other. And where do they go? They go up. They build mountains. So where's this happening right now? Right now. The Himalaya mountains are an example of a continental collision. I think it's also kind of interesting to notice that it happened in the United States once upon a time, right? The Appalachian Mountains were once a continental collision. But what happened? It was a long time ago. So they got softened. They're not craggy anymore. They've been worn down from erosion, right? From erosion. Subduction means what? Subduction. One plate connects with another plate. Which one? Continental, oceanic. What happens? The continental rides on top of the oceanic. The oceanic gets pushed under. That's subduction. Okay? After a while, by the way, what happens to that oceanic crust is it actually cracks off and begins to fall back into the Earth. And that's actually an important part of returning some of the heat energy to the Earth. Okay, spreading center. What's spreading center? When the plates are pulling apart and doesn't want to stay that way, doesn't want to leave a vacuum. So what happens? The magma comes up to fill the space. Okay, where is that happening? The Mid-Atlantic Ridge is a great example. Okay, it's happening in other places too, but that's a good example. Okay, hotspot. Sorry, hotspot. Hotspot. A little weak part of the crust, magma can leak up and make a volcano. Right? But when you have a hotspot, if the plate is drifting, then you can see not just a single volcano, but a chain of them. Right? So you can see in the Pacific Plate motion, a chain of Hawaiian Islands. And the interesting thing is, in the past, it was moving in a different direction entirely. Right? So the chain of volcanoes is the history of the movement of the plate and that hotspot leaking through. Okay, next one, transform fault. Where's that? Here in California, right? California, Santa Barbara, LA. Are we on the North American plate? We are not. Okay, we are on the Pacific plate, right? And that means that we're not on North America. Yeah, we are. Our plate is sliding across each other. We call it the San Andreas Fault. It's one of the faults, at least. And because of that, periodically it sticks and then it releases, and every time it does, we get an earthquake, right? So this is a simple idea on how earthquakes are generated, transform faults. Okay, the layers of the atmosphere: troposphere, stratosphere, mesosphere, ionosphere, right? Those are the four layers. Okay, nearest to the Earth's surface is called the what? Troposphere. Why do you need to know about that? What's special about the troposphere? It's where all the weather is, right? It's where all the water is, right? And what is water really good at? It's really good at insulating the Earth. It's actually the reason for the bulk of the greenhouse effects. So it's that troposphere that's really keeping the heat in, right? That's keeping the heat in, the greenhouse gases in the troposphere. Okay, troposphere, weather, clouds, water, where we live, okay? Next layer up, called the stratosphere. What's in the stratosphere? The ozone layer is there. Is the ozone layer good for us or bad for us? It's good for us. It's great for us. It actually blocks some of the sun's ultraviolet light. So because of that layer, we have much less ultraviolet light than we would have otherwise. The next layer up, above the stratosphere, the mesosphere. The mesosphere is a middle layer. What's good about it? I don't know. But we said something probably happens in this layer. Most of the meteors probably burn up in this layer. Okay, that's where they first hit some atmosphere that's more substantial, they burn up. Okay? And that's where you see the streaks then. Okay? The streaks of a meteor would be in that layer. And then we have the ionosphere. What's special about the ionosphere? Ion means what? Charged atoms. So these are charged atoms. It's the electrically active part of the atmosphere. It really responds to electrical stuff. Right? And one of the neat things I mentioned to you is you can bounce radio waves and so forth. Okay, but it's the electrical part of the Earth. There's a lot more to this, by the way. If you go and investigate, you can find some very interesting things. Like, I should have mentioned this, but the Earth has these interesting cycles and patterns that it does, and naturally, like breathing almost. Right? It pulsates with energy, and one of the pulsations is in the ionosphere. I'm not going to tell you that. But it's interesting anyway. Okay. Greenhouse effect. What's that? Greenhouse effect. The Earth is warmer or cooler than it should be. It's warmer than it should be without an atmosphere. With an atmosphere, we get a greenhouse effect. What are the gases responsible for the greenhouse effect? What's the most important one? Water is actually the most important. Methane probably is the next one. Third one, maybe way down. Third one, carbon dioxide. So even though we talk about it a lot, carbon dioxide is a really small piece of our atmosphere. But it turns out it has a big effect. So even though it's so small, it has a big effect. Okay, magnetosphere, what's that? The region near the Earth where the Earth magnetic field is meaningful. Okay? And so what makes the magnetic field of the Earth? The next line, the dynamo effect. Okay? So what's the dynamo effect? The circulation of charged matter is also known as electricity. It makes a magnetic field. It's really simple. Okay? And we're not trying to do, I mean, it's not simple. It's very complicated. We're taking a simple idea. Right? You can make a magnetic field by using electricity, electric current. Okay? This will happen in the Earth, in Jupiter and Saturn and Neptune and Uranus somehow, and in the sun we're going to find out next week, right? So it's happening all over the place. Solar wind, what's that? Solar wind. Charged particles coming from the sun, right? We'll study that more next week, by the way, when we talk about the sun. Where does it come from? Why is it there? Why is it sometimes really stronger? But don't worry about that for now. But what happens when the solar wind hits the Earth magnetic field? Can it penetrate? No, it gets deflected. Most of it gets deflected. Some of it gets trapped and spirals around the magnetic field lines. And where it's strongest, where is it strongest? At the pole, we see the energy of these particles given to the atmosphere. We get aurora borealis. And there's Aurora Borealis, Aurora Australis. What does that mean? Aurora Borealis. The northern lights that we see, and Aurora Australis is the southern lights. They're the same mechanism, right? Charged particles, lots of kinetic energy, hit the magnetic field, get trapped, and they spiral around, and they give up their energy to the atmosphere. Okay, tides. The tides, high tide, low tide. Okay, I don't know what else to say. High tide, low tide. What's high tide, low tide? The water comes in higher when it's high tide. The water goes out lower when it's low tide. Everybody seen it at the beach? High tide, low tide. Okay, when do you want to go tide pooling? Low tide, right? Low tide. You can walk around. You can find. Anybody seen an octopus? Isn't that fun? You can find octopus. Octopus. What's this? What's this word? Octopi. Thank you. I'm like, well, okay. Anyway, they're really fun. Not relevant. Okay. The tidal force is actually what causes the tides. What causes the tides? Everybody knows. The moon. No, not just the moon. The moon and the sun. They both cause the tides. But which one is more important for the tides? The moon, twice as important, right? So which one determines the high tide? The moon, right? The moon, and then across from the moon, right? So does everybody remember the picture? How many high tides are there? There's two. Where are they? Underneath the moon, and then on the far side of the earth. What about the low tides? They're in between. Is there a question on tides on your next test? Yeah. Okay. Anybody want to ask questions about tides? You know the name of the really strong, really high, really low tides? What's that called? Spring tides. And what happens is the Earth and the Sun and the Moon are all along a line, right? And when they are, then the Moon stretches the Earth and the Sun stretches the Earth in the same direction. You get really high tides and really low lows. But what about if the Moon and the Sun are working against each other? What's that called? Actually, it's coming up. That's the next words, right? Neap tide. Okay, so in that case, the highs and lows are really weak. They're just like almost no change in the tide. Tidal locking. What's an example of tidal locking? Give me an example of tidal locking. The moon, right? The moon is tidally locked. What does it mean? As it goes around the moon, what do we see? We only see one face, right? So that face is locked to the Earth, which means that it's rotating at exactly the same period that its revolution takes, right? It's the same amount of time. Craters, oh gosh, craters are holes in the ground. Craters, what makes them? Yeah, something. Meteors, something smashes into it, digs a hole in the ground, right? There's an ejecta. Craters, and where there are craters, there's lunar maria and there's lunar highlands. Where do you have a lot of craters, in the maria or the highlands? You're supposed to know this, okay? So the highlands are covered with craters. They're light in color. They're covered with craters. Are they old or young? They're very old, right? Whereas the lowlands are flat and almost no craters, and they're dark in color. And those are called the maria. Okay? So the dark areas of the moon. The dark areas we said before are an example of magma flooding. Okay? Magma flooding. Late heavy bombardment, you're supposed to just memorize when that was. It was a period of time when everybody on the inner part of the solar system was getting hit by debris. Okay? It happened about how long ago? 4 billion years ago, about 4 billion. And the giant impact hypothesis refers to what? The formation of the moon, right? And we know that there's two theories that we don't like. One was called the capture theory, right? Where we captured the moon. Another was called the fission theory, where it spun off. The fast rotating moon the fast rotating Earth spun a big chunk of material off and formed the moon. Neither one of those is right. The giant impact hypothesis makes the most sense. So what happened? A Mars-sized object that big crashed into the Earth. Most of it was taken into the Earth itself, but a significant amount of material splashed out into a circular orbit around the Earth, and then gradually over time it coalesced to form the moon. Okay, that's our story. I'm sticking to it. That's it. Okay, going down. How much stuff is left, right? So I just do a quick example for you. You should know how to do this. How do you do a half-life problem? They're pretty simple. If I tell you the half-life, you use that information. So for example, Suppose I tell you the half-life is 500 years. Okay? And I start off with, I start off with 32 kilograms. Okay? Start off with 32 kilograms. Okay, so the question might be, how long will it take? How much time will have to pass before you're down to hard? Okay, down to 4 kilos. When will it be 4 kilos left? When will it be 4? How much time has to pass? So the idea is, every time you wait for one of these half-lives, you wait one half-life, how much radioactive material will be left? Half of it, right? So 16. Wait another half-life, and it doesn't go away. Half of what you have goes away, right? Every time, it's always just half. So you go down, now you're down to 8, and wait one more half-life and down to what? Now you're down to the 4, okay? So how many half-lives did you have to wait? 3. You had to wait 1,500 years. You guys see how it works? 1,500 years was the answer. After 1,500 years, it's going to be only 4 kilos of this radioactive substance. What happened to the other 28 kilos? Did they disappear? They're still there, but they turned into something more stable, right? They're still there enough, right? You don't lose the matter. Okay, so that's a quick example. Whoa, look at screensaver. Questions good? Okay. Okay, so determine the amount of, okay, how to plate tectonic plates in different formations. I think general. So we don't have to do it all over again. So the five processes are continental solution, subduction, constant, what am I forgetting? Transform fault, one more. Oh, stratosphere, thank you. Okay. The layers of the atmosphere, troposphere, next one. Stratosphere, next one. Mesosphere, last one. Ionosphere. Okay. Describe how the magnetic field of the Earth functions. Makes the magnetic field. The solar wind tries to get at that. The magnetic field deflects it, and then and we just did this too, right? Oh, so think about that. And okay, compare the strength of gravity from the sun and the Earth. Which one feels more strongly on the Earth? The sun does. Which one has a bigger tidal force? The moon, right? So that's a distinction. And then the features on the moon formed, and what they tell us about the relative age. I think we did that too, right? The old areas are up, highlands, lots of craters, so lowlands are fresh and new, relatively new. Okay, the orders of the layers and their approximate size. You don't have to. I changed that. I guess I was trying to feel a little ambitious. But what's the period of the moon? 27.3 days to go once around. 27.3 days. Okay. All right, chapter 5. You guys still here? Are you done? How do you want to hear the questions now? Okay, do the question. Yeah. Okay, let's go. Question 1. Question number 1. Comet, the orbit near the elliptic plane in an orbital period of 75 years is mostly comes from the. Okay, try that out. Is it working? You guys put? Okay, where does it come from? I can see your result. we good? Now we click it. Okay, I can see the results. Alright, so on the aggregate, oh, it works. Okay, cool. Alright, we use right. That's right. Chemical. If it's less than how many years, it came from the chemical. 200. Okay, chemical. If it's more than 200, it came from way out there. Okay. Number two, according to the accretion model, when dust grains begin to stick together, there's this little tiny dust grains. The force that initially holds the grains together is in static electricity, the strong nuclear force, gravity, or magnetism. Which one do you think? All right, we got it. You click something. All right, 1, 2, 3. All right, you said static electricity. Ooh, what you got? It's static charge. They're so small, gravity doesn't matter. But the charge matters. So positive and negative work, even when they're tiny. In fact, it's better when they're tiny. Okay, number three. What is the main reason? What is the reason that Io or Io, the moon of Jupiter, is the most volcanically active body in the solar system? This is an actual question. Okay, this is your test question. Why am I doing that? All right. What is the reason? Meteors from the asteroid belt are constantly bombarding it. The core is the most radioactive solar heat. Tidal forces from Jupiter. It is enormous and has a huge amount of thermal energy from the initial formation. All right. What do you think? What's the right answer? Okay, are we good? See how we did? Okay, hopefully you got that one. The right answer was D, tidal forces. Okay, so none of the other answers make sense. Sorry. It's a small body, so it should have cooled off, but it didn't because it's being heated by Jupiter's tidal forces. Tidal forces are heating Jupiter. Number 4. Which of the following has most strongly shaped Venus's surfacing? Surface, yeah. What has shaped Venus's surface? Weathering, seismic activity, volcanism, cratering, or let me mention to you that we don't have any evidence of none. So I can throw out a couple of answers, right? What comes from plate tectonic? From transform faults, right? Seismic activity from that. Weather, probably. Is it the most important factor? And the answer is no. The most important factor is volcanism. Okay, volcanism. Volcanism. Sorry, volcanism. C-type asteroid. Ooh, remember that? C-type asteroids differ from S-type and N-type. In the C-type asteroids, never underwent differentiations, are more numerous. Ooh, wait a second. Ooh, shoot, I messed up. Oh, shoot. Holy crud, did I really do that? Yeah. There's 2 right answers. Yeah. 30? Okay, what's one of the right answers? I can't believe I did that. Holy mackerel. Okay, A and B are both right. What the heck can I put that on a test? Okay. Oh my god. Well, anyway, which one's right, A or B? C and D are not right. Okay. Why does Mercury have a thin layer of hydrogen and helium near the surface? They are outgassed by rocks. These gases are released during impact. Other elements move fast enough to escape Mercury's gravity. Mercury temporarily traps solar wind particles. Can I read that now? Okay, and you said Mercury temporarily. Ooh, good job. Okay. The principal component of Venus's atmosphere is what? Did I start it already? Can you click? Yeah, okay. The principal component of Venus's atmosphere is which one? Okay, so pretty good. So is it nitrogen, sulfuric acid, carbon dioxide, or water? I still told you about the effect on Venus. You learned a little bit more. It lost most of its water in that effect. But anyway, the right answer is carbon dioxide. Take carbon dioxide. 100% carbon dioxide. The cloud layer is sulfuric acid, but the atmosphere part, the clear part, is carbon dioxide. The following solar system moves as geysers spouting liquid water. Liquid water. And I told you a little story about Cassini flying through one of those geysers. That's the way they do that. Okay, this is really special. Okay, all right, good. And he said, hopefully you remember Enceladus. Ooh, most of you did. Titan does not. Titan has the mountains in the atmosphere and the rivers, but they're not spouting. And Enceladus is spouting. Okay. Also, what is not a reason the Earth core is still hot? What is not a reason? Write these down. Which one is not a reason? Everything else is not. Okay, and about half of the energy is still there from the initial formation, or maybe 45% anyway. 45% from radioactivity K5, that's the cross, so solar energy is the answer. It didn't come from solar energy. I'm going to give you Can we do the list? Which one? Number 5. See, I need 6.
Five sheets.
I skipped 5?
Yeah.
Oh, I did. I'm sorry. Oh, I did. Oh, yeah, let's do 5. That's right. Ooh, how did I skip that? Okay, here we go. Number 5. This mission by the European Space Administration recently visited the also known as 6017, learned a great deal about comets that we did not prove. But Cassini went to Saturn. We just learned about that. Juno is currently at Jupiter. Messenger went to Mercury. Voyager has left the solar system. So the right answer is Rosetta. Did you get Rosetta? Everybody knows. Ooh, very good. Okay. We'll go back to chapter 5. You all sign in to get in. Let's keep going with chapter 5. Let's go with chapter 5. Cassini went to Saturn. That was that video that we watched. Yeah. Okay, chapter 5. Chapter 5. Chapter 5. Okay, so we're on chapter 5. Or final chapter. Sure. Take a bathroom break. 5. 50 bathroom break. It'll be a quick final chapter here. Anybody have questions before I cover chapter 5? Remember that? Number 6. There's 2 right answers. There's 2 right answers. The 2 right answers. Pick either one of the right answers, and you'll get credit. Asteroids, and they are also the most common asteroid in the asteroid belt. So both the M and the S, you know what the M stands for? M-type asteroid. M stands for metal, and S stands for silicate. So those are the 2 types of asteroids. They form when a larger asteroid comes apart. And so that larger asteroid actually underwent differentiation. You got a metal core and a silicate mantle, and then it got broken apart. You got a bunch of M-type asteroids and a bunch of S-type asteroids. They're called families of asteroids. Anybody else? Another question? Questions? Anything? Bothering? Concern? There's a lot of stuff. Yeah.
I know you said that you didn't have to know what the size is.
No, you don't need to.
Is there anything?
You don't need to know the size. What was that?
Was there anything else that you said before that you don't have to know?
Okay. Well, the only thing I didn't put up there, I did, maybe it's heat. I don't know. The atmosphere of Venus, I definitely didn't find that on the sun. So that's kind of, I don't know what happened. You're supposed to know that. You're supposed to know that it's really so hot the surface of rain undergoes there. Yeah. Sure. Okay, so we're not going to complicate, we'll keep it around science. But the idea is that electricity can create magnetism. And so in fact, it's called an electromagnet. So the concept of an electromagnet is really easy. You take electricity and you make it go on a loop, and that will create a magnetic field out of it, like a bar magnet, very much like a bar magnet. So the trick is you need something that conducts electricity, and it has to move in a circular path. That's the trick. That is really the start. So once you have those two ingredients, you can have a dynamo. So in the Earth, yeah, however you circulate, it doesn't really matter. It's got to circulate, and it's got to be that conductor. So in the Earth, you see metal in the core. That's perfect. Except part of the core is solid. It doesn't move. It's the outer part of the core that is so molten that it's generating a dynamo. So in the Earth, it's the rotation of the Earth, means that metal in the Earth has some charge to it. And by the way, don't probe too deeply because it's pretty confusing. But anyways, the idea is that molten metal conductor is generating dynamo for the Earth. And actually, for most of the construction like objects, that's what would be the way. So Mars, when it had one, same idea. It was rotating, and it had a hot core of molten iron. And when you get out to the giants, which have even bigger magnetic fields, the cores are completely solid if they're in the core. Right? And so we have to come up with another type of conductor. What they came up with is metallic hydrogen. So if we didn't have metallic hydrogen, really, we would have how the heck does it make it powerful? You have to have some kind of conductor. And so it was really an incredible revelation that hydrogen can be made like metals. And it requires, in order to do that, incredibly high pressure. So if you study the pictures of Jupiter and Saturn, metallic hydrogen is not everywhere. You have to go deep into the planet. So the layer of metallic hydrogen is around the core. Above that, we have liquid hydrogen and helium. And then above that, we have gas hydrogen and helium. So none of that conducts electricity, it's just in the metallic. So why did Uranus and Neptune not get that? They have hydrogen and helium, but they don't have enough pressure inside to generate the magnetic, the metallic hydrogen. Sure. Okay, are you ready? Chapter 5? Okay, chapter 5. Kuiper belt object. What's a Kuiper belt object? An object that's in the Kuiper belt. So now the trick is, where is the Kuiper belt? Where do you find it? It's past the planet Neptune. It's all the way out there, right? So we sometimes talk about trans-Neptunian object. Something is past Neptune's orbit. That's where the Kuiper belt is found. Any object that's out there in the Kuiper belt is called. Okay. Exoplanet. Exoplanet is a planet around another star. Okay. How do we know they're there? Because, right? We have some ways. We'll talk about it in a second. A dwarf planet. What's an example of a dwarf planet? Give me an example. Pluto. That's a perfect example. Pluto is a great example. And you want to remember, if you can, what makes it a dwarf planet. So there are three things that make a planet. Number one, remember, it goes around the star. Pluto goes around the sun, right? Number two, it's large enough to be a sphere in shape. Pluto's a sphere, right? The first two things, Pluto's fun. But the third one is it sweeps up the orbital path of debris. So the path that it's following around the sun doesn't have a lot of debris. Pluto goes through the Kuiper belt, which is just full of debris, so we say it fails. And then anything that is the first two and not the third one is called a dwarf planet. So a planet that goes around the sun is big enough to be a sphere, but doesn't stick out its orbital path.
Wait, that's because it should track the material.
Yes, exactly. That's the reason. If it was a little bit larger, it would have been more effective at clearing out its orbital path. But it's not big. But yeah, it's pretty small. But there's probably 1,000 Plutos on. So we kind of keep that in mind. That's another thing we can call the water percent. Then you don't have to memorize 1,000, just 8. 8 is much easier than 1,008. Okay, asteroid belt, where do we find the asteroid belt? Between Mars and Jupiter. And now, again, don't, you're in the astronomy class, most of the asteroids never got together with another year. Why not? And the answer is Jupiter's force, the force of Jupiter's gravity, tidal force and force, prevented them from ever getting together. So it's really Jupiter inhibited the growth of the planet in that area. And so that's the raw material. That's the raw material that the solar system started with. So when we look at an asteroid, that's another name for it is a planetesimal. That's what a planetesimal is. Asteroid. Okay, that's what it looks like. And then you go from there. We'll talk about that in a minute. Okay, standard disk, what's that? It's a kind of a donut-shaped ring that goes around the Kuiper belt. It's a new thing. I don't really know much about it. We don't know much about it. It's still hypothesized. But we think it's kind of an intermediate stage past the Kuiper belt before the Oort cloud. Oort cloud, way far away, really far away. Thousands of, tens of thousands of light AUs from the sun, and it's spherical in shape. And that's where the long period comets come from. Okay? We see those. We have long period comets that have 2 million year periods. It took 1 million years to come in, and 1 million years to go back. Another 1 million years, they'll come back in 2 million years, and then they leave. Terrestrial planet. What's it? I actually said it. Yeah, it's the donut shape. It's ring. It's a ring that goes around the country. And it's hypothesized. We actually don't know much about it. And this is the first time I've ever included it in the study guide. It's just the structure in between the Kuiper belt and the Oort cloud. Further than the Kuiper belt. Okay? The Kuiper belt is really a disk. And it's kind of just a little bit more like a donut. For us or something. A terrestrial planet, what's that? Rocky, right? Iron, rocky. Where are they found? Close to the sun. There's 4 of them. They are Mercury, Venus, Earth, and Mars, right? Okay, the next one, gas giants. How many do we have? 2. What are they? Jupiter, Saturn. Ice giants, Uranus, and Neptune. Okay, those are the names. What makes them ice giants and gas giants and terrestrial planets? Their composition, largely, right? And what they're made of is partly where they go in the solar system. But also, the gas giants, we think, probably started first, formed first, found a core, made a core, and then gathered together the hydrogen and helium. Okay, uncompressed density. Well, what the heck is that? The idea is if you take the total mass, divide by the total volume, you get the average density. And if you look at the terrestrial planets, are they more or less dense than these ones here? And we studied a little bit, and they are more dense. These ones are more dense than these ones. What's the least dense planet in the solar system? Saturn happens to be. And Jupiter and Uranus are almost the same, right? And Neptune's just slightly higher, but they're all less dense than the terrestrial planets. The terrestrial planets are more concentrated, right? More dense. Planetesimals. Okay, so I actually got to planetesimals. What's a planetesimal? One of the early fragments that was in the solar system. Stage of the accretion model. And I think we'll end up talking with the wrong computer. Okay, planetesimal would be a small chunk of matter left over from the early solar system. And those pieces went together to form a protoplanet and then eventually a planet. Okay. And I'm past the top. So we're supposed to leave. You guys done? You want to say? Here's your hand saying. Okay, I can take too much longer anyway, so just a few more minutes, okay? We'll try to get it done as much as we can. Trojan asteroids, who knows what those are? Trojan asteroids are found in very special places. Actually, maybe I should draw a picture to remind you or bring it up. Let me draw a picture, okay? Easier. Where are the Trojans found? They are found, the first ones were found around Jupiter. And actually it's connected to the next question with Ron's point. So let's draw that together. Sorry about that. I have no ring. Okay, so actually, why don't I do the Lagrange points first, because then it'll be easier. Okay, what are the Lagrange points? If you start with the sun and Jupiter, okay, and you draw a little picture, right? There are special mathematical places where the gravity of the sun and the gravity of Jupiter work together. And these are known as the Lagrange points. So one of the points is in between Jupiter and the sun. You can kind of think about that. Jupiter pulls one way, the sun pulls the other way. They're working together. There's a special point. That one's called L1. Okay, L1. There's another place just beyond Jupiter out here. It's called L2, right? And the gravity from Jupiter and the sun are working together to allow this thing to happen. And then on the other side of the sun, there's another point called L3. And then these are where the Trojans are located now. If you go away from Jupiter 60 degrees in front and behind, you get to these Lagrange points, L4 and L5. So something special with the gravitational force from Jupiter and the sun works together to allow objects to orbit with Jupiter, right? To stay with Jupiter. So these asteroids, we have discovered thousands of them that are just hovering right there, some of them in front of Jupiter's orbit, and some behind Jupiter's orbit. So they confirmed that this guy Lagrange was right. These are real places. These 2 points are stable. The other ones are unstable, but we use these other ones as well. Okay, L1 and L2 especially. Okay, so we hit those 2, Lagrange points and Trojans. All right, and the next definition. Earth crossing asteroids. What are those? Asteroids that cross the orbit of the Earth. They could potentially hit the Earth, by the way, right? Will they? Actually, NASA says not for a while, but eventually they will. Okay, they're going to hit, but they have a possibility of hitting the Earth. That's what's an Earth crossing asteroid. Okay, so you don't worry about it. Nothing to do. You know, we die, but we're here now. Let's enjoy today. Okay. So, but what happens? Differentiation. We skip that. Don't worry about it. Okay. Differentiation. What does that mean? We see that some of the asteroids are large enough to have gathered together a little body and be almost like a protoplanet or a dwarf planet. There's a couple dwarf planets. Right? The biggest dwarf planet in the asteroid belt, you might know that. I have it up there. I don't think I do. Oh, I think I have it later. Ceres. Ceres is a dwarf planet that's found in the asteroid belt, and that's a pretty big size object, a couple thousand miles across. So what does it mean to differentiate? It gathered together enough material to be hot enough to be molten, and then the layers separated. Right, the densest layer is going to be iron and nickel, and then silicates and then rubber. Okay? So we have 3 different types of asteroids: C-type, S-type, M-type. C-type, carbonaceous, right? They haven't changed. They've never got together with anybody else. They're the raw stuff that everything in our solar system was made of. Lots of organic compounds, carbon rich. S-type is silicate type, and M-type is metal type. And those came from larger bodies that must have been broken apart in collision. Okay? So if you differentiate, your core is metal, and the outer layer, the mantle, is silicate. And if you get smashed apart, then you end up making a bunch of M-type asteroids in the middle from your middle, and a bunch of S-type asteroids from your mantle. Okay, so do you get more S or M? It's going to be more S types. Okay, and that might explain why there's the most is C, the next most is S, and the least common is M. Okay? Snow line. What's the snow line referred to? The place where ice can form, or water ice can form, and that's about 4.5 AU, we said. Okay, if you find different, actually, you can find another term of that. I'm just leave it. Forget it. It's fine. It's just a number. Albedo refers to reflectivity. So high albedo means what? Reflects light well. Low albedo, dark, doesn't reflect light well. Comet nucleus, right? We're talking about a comet right now. The nucleus is the hard stuff, the solid material of the comet, the core of the comet. And then what happens to a comet? A comet rides on an orbit around the sun. You made a comet in class, right? The idea was that the comet, when it gets closer to the sun, is getting the energy from the sun, and the solid turns into a gas. And that process is called sublimation, right? So sublimation is occurring. You form a cloud around that comet, which is called a coma, right? And then that even will make the tail as well. Fragments of the comet will be blown out as jets of material come out of the comet. And we saw that with the Rosetta mission, okay? And then the comet tail has two pieces, right? The ion tail and the dust tail. And you're supposed to know that one of them is straight and one of them is curved. Which one is which? So the ion tail and the dust tail both point in which direction? Away from the sun, in the direction of the solar wind. But the ion tail is interacting more strongly. It's made of ion. It feels a stronger force from the solar wind. Straight. And the dust tail is going to be neutral matter, pieces of dust and particles. So it kind of remembers where it was. It's a little curvy. Okay, short period comet, less than 200-year period. Okay? 200-year, and for example, Halley's comet, 76 years, 75.3, whatever, is a short period comet. Long period is more than 200 years, but it can be really long, billions of years, right? Rosetta mission, we just mentioned, right? Went to Churyumov-Gerasimenko and dropped a lander and learned lots and lots of stuff. We actually learned probably more than we ever knew before about comets just from this one mission. And what did it do? It rode with the comet as the comet went around the sun, and it watched all the stuff happening on the surface. It's really exciting. Meteoroid. Who knows what a meteoroid is? An object that could enter the atmosphere, called a meteoroid. If it enters the atmosphere and we see it streaking across the sky, we call it a meteor. Meteor. And then meteorite means what? It landed on the ground and you pick it up. It's a meteorite. What about bolide? Oh, I dropped fireball. Oh well. Bolide. Bolide means what? It explodes, right? So why does it explode? Because it comes down to the atmosphere, it gets hot, right? I know, actually I shouldn't ask any stuff, never mind. I was going to ask if anybody knows how it gets hot. Is it friction or compressional heating? Okay, the right answer is compressional heating, mostly compressional heating. Anyway, if it gets hot enough and a little gas bubble is inside of it, that gas bubble can blow up and you get a bolide. So that was the example I showed you with the Chelyabinsk meteor in Russia. It blew up over the city and then the shock wave blew out windows and everything. Oh, it's kind of cool. A meteor shower, is that something that you can predict? Number one question. Yes. And so meteor showers are on astronomy calendars. You look them up. And the reason they're predictable is they happen at the same time of the year, every year, right? And so what is happening? The Earth is passing through the debris left behind by a comet, right? That's what it is. We're flying into comet dust. And we have a meteor shower the same time every year. Do meteors come predictably? Like, do we know there's going to be a meteor tonight? Not when and where, right? We don't know them, but meteor showers we do. Regular meteors, random. Meteor showers, we know. Okay. Interstellar gas means what? The gas between the stars, right? This is the stuff that will make stars one day, by the way. Right? It will make one, and actually we'll get to that too. Center of mass. Talking about center of mass. Who knows what that is? You take two masses. Actually, there's a question on your test. Can I give you a hint? You guys want a hint? You guys stayed all the way till the end. And you here, live audience. Oh yeah, there's a guy right here. Evan, the sound is distorted when you move to the right side of the screen. Really hard to hear. Okay, sorry, Evan. I will try to talk more clearly. All right. So that's cool though, right? Okay, so center of mass. If you take an object which has a mass of m, and then I take another object which is twice as big, I'm going to try something simple with you, okay? And I ask, where is the center of mass? Okay, the trick is you draw a line between them. Okay, and where is it? Is it right in the middle? No. Where is it? Closer to the big one or closer to the small one? Okay, it's closer to the big one. Now here's what a lot of students will say. Well, it's closer to the big one. It's right there. But if you look, you see this one is twice as big, but it's not like 50 times as big. Okay? It's only twice as big. So mathematically, it's not going to be quite so close to the big one, but it is going to be not in the middle. It's going to be closer to the big one like that. Do you guys get the idea? So you have to compare these two. Now, what if I had said 20 times the mass, right? Then where would you put the center of mass? You'd put it right here, right there next to the big one. You understand that? So the bigger this one is compared to this one, the more the center of mass moves towards its center. Yeah. No, just estimate. Okay, but if they're equal, where's the center of mass? In the middle. And if they're not equal, estimate. Okay. But I mean, clearly, unless there's a huge one, you got to think, is it really that close to the center of mass of the big one? Okay, don't pick that answer, right? It doesn't make sense. Okay, Evan, did you hear me okay? All right. Just kidding. All right, here we go. No, I'm not kidding, Evan. I care about you right now. Right. I wonder if he's still on, though. He might. Okay, here we go. Next one. Center of mass, radial velocity method. Okay, there's 3 methods. Let's just review. 3 methods for finding an exoplanet. 3 methods, right? So one is called the radial velocity method. One is called the transit method. And then the third is called direct imaging. Missing. Okay, because it's not very good. I guess I draw. I don't know why I put that. Okay. So which one is the best one? The transit method, the best. Which telescopes use the transit method to detect thousands of planets? It's called Kepler. Okay, Kepler Space Telescope. So this is the most effective method we've ever had for finding exoplanets. And how does it work? The transit method works by watching a star continuously. You just watch it, and you monitor the brightness. And what happens when the planet goes in front of it? It makes it dim a little bit. And this is called a light curve. Okay, so the transit method watches the light curve and sees a little dip, and then it goes back to normal again. And so from this, you can figure out the size of the planet and where it is, and it's pretty cool. And it works super effective. Yeah.
Does that curve ripple or?
Yeah, it's incredibly cool. If you look at real data, you're like, what? It's pretty cool. By the way, there's actually something called citizen science. Like if you just said, like right now, I'm gonna go help find it. There's actually a program where you can go look and see if you can identify the little green bit, and you can learn how to do it. Like I'm not kidding. So one of the companies is right here in Tokyo. They need help. There's so much data that the computers can't even crunch it all. And the computers mess up. They throw out really good stuff because they reject it. They say, oh, it's so good. But in fact, a human being can find it when computers can't. So you have value. The computers have not overrun it yet. Okay. So transit method, most effective. The next most effective is called the radial velocity method. And that one is kind of based on the center of mass idea. So the radial velocity method says that if a planet is orbiting a star, they're actually not orbiting a star, it's orbiting the common center of mass. The star has to orbit that center of mass as well. So planets cause stars to wobble. Bigger planets cause bigger wobble. Closer planets cause bigger wobble. We measure the wobble because the star goes towards us and away from us. And when it does, the light changes just a little bit by using the Doppler effect. So if you remember, when something is coming towards you, you see a higher frequency. When it's moving away from you, it's called a blue shift. When it's moving away from you, you see a lower frequency called a red shift. Okay? And so that's the method called the radial velocity method. Pretty good. Okay? Super Earth. What's a super Earth? I didn't go into this too much. It's a bigger body than the Earth, maybe up to 2 times the size of the Earth. Right? It's called a super Earth. And habitable zone. We talk about habitable zone. I don't know if I talk about it too much, but a little bit maybe. No, not much. What's habitable zone? It's the region where liquid water can exist on that planet. And every star is different. So a big bright star, you got to get far away before you get into the habitable zone. A very dim star, you can be really close. We have a pretty broad habitable zone. All right, so hot Jupiter, what's hot Jupiter? Hot Jupiter. It's a planet, an exoplanet, which is close to the star and has a very large mass. So what is it called? A big wobble. So the radial velocity method, which is measuring the wobble of the star, is really good at finding hot Jupiter. Not so good for finding Earth, right? Because Earth is too small to make a big wobble. Does that make sense? So the bigger the planet, the stronger a pull on its star, the bigger the wobble of the star will be. The radial velocity method is more effective. So they find hot Jupiter. Hey, conservation angular momentum. The solar system formed somehow, right? A star was formed from what? What started the star formation? A shock wave, a jet of another star. Star died, and then it dying red goes shock wave, and that shock wave makes a little area in the interstellar gas that's just slightly more concentrated. And it's like a seed that will then begin to gather matter into itself. So it's a big cloud, more than the size, anybody remember? About 1 light year across. And what happens when it collapses is you get a much smaller thing, a solar system. So when it collapses, it had a little swirl when it started, but by the time it collapses, what happens? It rotates really quickly and flattens into the shape of the disc. Right? And that is called conservation of angular momentum. We keep saying those words, but yeah.
Is the orb cloud still like?
It's about linear, yeah. Almost, yeah. And that's why it's not in a fixed shape. It never really collapsed. It's there, and I guess it's still gravitationally connected, but not very strongly, just weakly. Yeah. That's a weird thing. Actually, even never mind. Get out of Okay, protoplanetary disk, condensation. Okay, condensation period. Okay, so we have little grains of dust that ultimately are going to make it. And so there's a sequence of the dust, right? If you remember, when you're closest to the star, what kind of dust can form? Little tiny grains of what can form, even though it's hot? Metal and metal oxide. Those two grains are formed first because they can exist even at high temperatures. You go a little bit further, and it gets cool enough that finally you can get silicates. Right? The silicate crystals can form SiO2. So it's metal, silicate, and then 4.5 AU, we said water ice can form. And then further out, I didn't tell you exactly where you get the other kinds of ices forming. So we just did those 4. There's really many more. We just did those 4. So that sequence tells you where the grains will be. So where do you find metal grains in the solar system? Are they just close? No, they can start close, but they can go anywhere. The whole solar system is full of metal grains. Where do you find silicates? A little bit further and out, you find silicates. Where do you find water? A lot of water past 4.5 AUs and out. And then finally the other ice. Okay. Condensation theory, protoplanetary disk. We kind of mentioned that. That's the disk that forms as the first. The thing is collapsing into forming a star. It's not a star yet. What do we call it? A protostar, right? It's not a star. It's glowing because it's hot, but not because it's making its own heat energy. Not because of the formation energy, right? When it collapses. Interstellar dust grain, I don't know, whatever. Ignore that. I don't even know what. Just whatever. Just core accretion model. Okay. What's the core accretion model? That's referring to Jupiter and Saturn. In order to make such a big body, what did you need to do? You had to have a good solid core so that there's a gravitational force which could then gather together the hydrogen and helium to make a big body like Jupiter and Saturn. Okay? Wrong computer again. All right. Okay, lots of things. I think I've covered most of these now. Let's see if we can. Terminating comment. We did that already. Where did it come from? Short period, Pepper Bell. 200 years, right? Long period, 4 times longer than 200 years. Okay. Identify the ion and dust tail from a picture. If I show you a picture, which one's straight? Ion tail, right? Which direction are they both pointing? Away from the sun or the direction of the solar wind. Good. Explain using the condensation theory how the different planets came to have different compositions. Okay. So which planets are going to have metal in them? Just the inner ones or all of them? All of them, right? Every planet has one. Which ones have silicates? Well, again, pretty much every planet. But you get more if you go further away from the sun, right? There's going to be more. Which ones have water ice incorporated in their structure? 4.5 of each. Jupiter, Saturn, Uranus, Neptune. And which ones have the other kinds of ice? That's pretty far out. So Uranus and Neptune, definitely, not so much Saturn and Jupiter, right? Conservation of angular momentum. We get through that. What's important about that again? Big bang swirling a little bit, collapses, has to swirl very quickly. Okay? And then, so what does it mean? The planets that formed were in this disk. So which direction do all of the planets go? The same direction around the sun. Right? What about their rotation? It's the same general direction, same kind of angular momentum. Which way do their moons go? The same direction around the planet. Right? It's all the same direction of angular momentum. So that's good. But when we find things that don't match that, that's a clue that they weren't born there. Right? Something happened. Estimate the location of the center of mass. I did that over here for you. Good? Okay. Explain the activity of a comet on its elliptical orbit. So comet, what are the two words that you're going to talk about with a comet? Two words. Perihelion and aphelion. Okay, let's talk about those words. So where does the comet feel the most heat? At perihelion. So what's going to happen to the activity of the comet as it approaches perihelion? It's generating more heat out from the sun. You're going to see the coma develop. The tail develops. It's going to get bigger and more impressive. And then it starts to move away from perihelion towards aphelion. What should happen? The tail will shrink, the coma will shrink, and when you're near aphelion, it doesn't have a coma. It doesn't even have to be that far. When you go towards aphelion, the coma goes away. Where does it go? The coma, which was the atmosphere around the comet, where does it go? It drops back down onto the surface. Right? This is what happens. All right, so I'll explain heating and lighting. Okay. Oh, I did tell you that. So meteors stream through the atmosphere. They make a streak. What's the streak coming from? The burning of meteor. No, it's the atmospheric gases getting excited by the energy of the meteor. Right? It's the atmosphere that's glowing. Okay. Explain the explain M type and S type. I did that already. M from the core, S from the mantle. Describe the different methods of exoplanet. I kind of did that too. The best one is the transit method. The weakest one is the direct imaging. Okay, which wasn't in the study guide at all, but there it is right there. So maybe you still kind of know. And have we ever seen a planet directly? Direct imaging? Yes, about 20. That's it. Right? It's really difficult, but the technology is getting better. Maybe it'll change. Explain. Oh, I didn't tell you about that. Anybody know why TRAPPIST-1 is so cool? You guys are here. I'll tell you. TRAPPIST-1 has more than 8 planets. It has about 7 to 8 planets, maybe 8. Oh, 7 habitable. 7 habitable planets. 7 planets in the Goldilocks zone. So what are the odds that we're going to find another planet that's in the Goldilocks zone that we could live in? That we could live there, right? It's actually, if we could get there might be planets that we could live in. Okay, and the asteroid Ryugu, you're supposed to know that name. And we watched, I don't think I showed you guys a little video clip, right? Just by accident. It was dropping down on the surface and grabbing a sample and flying away. And it also dropped a little lander that was hopping around taking pictures. Okay, blah, blah, blah. Where are the planets? In order: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Okay. Where's the Kuiper belt? Where's the asteroid belt? Asteroid belt is between Mars and Jupiter. Kuiper belt, past Neptune, Saturn, past the Kuiper belt, Oort cloud, past that. Right? Oort cloud is the outermost thing. You do want to know roughly where these are. Lagrange points, we erased the picture. Oh, no. Okay, but anyway, we did that already. Lagrange points, there's 5. 5 Lagrange points. No, probably where they are. Oh, that's it. Oh, good. We're out of here. Good luck tomorrow, guys. We'll see you the mañana. That's it. I'm done. Stream is out. That's longer than it was supposed to be. I'm late. I got to go to class at 7. Oh, man. UDT, how are you getting there? Oh, good. Can I get a ride? Just kidding. I'm just kidding. Oh, man.